Hello everyone. I want to go over another problem in graphs now called the traveling salesperson problem. So the goal of this problem is to say, okay, given a graph with some vertices and some edges, find a permutation or a shuffle of the vertices so that each adjacent pair of vertices is connected by an edge in the graph, and the sum of all lengths of edges is minimized. So that is our goal of the traveling salesperson problem. So here's a graph, and let's look at an example and see if it satisfies the conditions here. So let's say that I gave the shuffle, maybe I'll say 1, 2, 4, 3, 7, 5, 6, 0. So first thing I got to check, is that actually a shuffle? Is that a permutation? And yeah, so I have 8 vertices here, and that is indeed a shuffle of the 8 vertices. No vertex is repeated more than once. Okay, the other thing I got to check is, are these actually edges in the graph that I was given? So let's see. So 1 to 2, yes. So I'm looking at the adjacent ones here. 1 to 2. And let me go ahead and actually change the color here. Okay, so just to keep going here, so 1 to 2, 2 to 4, that is in the graph. 4 to 3, that is in the graph. 3 to 7, that is in the graph. 7 to 5, that is in the graph. 5 to 6, that is in the graph. 6 to 0, that's in the graph. And technically, we should actually say, for the traveling salesperson problem, we should also consider the edge from the end to the beginning here. So it actually creates a cycle that's known as the Hamiltonian cycle. So let me go and show you what that cycle looks like then by highlighting those edges. So there's the cycle that I pulled out. And okay, so that certainly satisfies the first conditions. It's a permutation. Each adjacent pair of vertices, and I should say including the last and first, is connected by an edge in the graph. And the sum of all lengths of edges is minimized. So that's the thing I'm not sure about at this point. So it certainly is true that I've given you a permutation that is actually in the graph, that has all the edges. But how do I know that the sum of the edges is actually minimized? And so that's what makes this problem difficult, actually. Actually, it's already hard enough just finding a cycle in the graph. That's called the Hamiltonian cycle problem. It's actually an NP-complete problem. But this is actually what's known as an NP-hard problem. What it means is if we could solve this problem, if we could solve this problem efficiently using, say, a polynomial time algorithm, then there's a whole host of problems that we could solve that we think are hard. So what I would like to show you actually is a way to approximate a solution to this problem using minimum spanning trees and depth first search, actually. Okay, so let me take a second here to clear this graph. All right, I've cleared the graph because now I want to look at a special case of graphs called complete graphs on a metric space. So a complete graph on a set of vertices in a metric space is a graph with all possible edges between all pairs of vertices. So that's the complete graph part. But it also satisfies the following property. So the edges satisfy these metric constraints. So I would say that the distance between u and itself is 0. The distance between u and v, so these are the distances of the edges, right? So the distance of the edge from u to itself is 0. The distance of the edge from u to v is equal to the distance of the edge from v to u. Now in this case, we're using an undirected graph, so that's a bit redundant. But the one that's really going to help us at a moment is that if there are 3 vertices involved, what we would say is the distance between u and w, or this between u and v, is less than or equal to the distance between u and w plus the distance between w and v. So just as an example of that, I'm saying here, I can do any pair of edges. So the distance between 7 and 2 is less than or equal to the distance between 7 and 3 and 2. That's called the triangle inequality. So that's going to help us in a moment. So you can see it's a triangle inequality because it makes a triangle, and the idea is somehow that it's like, why do we always take shortcuts when we can? Why do we cut these corners? Well, because if you were to go through the corner, it would take longer, potentially. So that's the triangle inequality. All right. So that's called a complete graph on a metric space. And so now what I want to do is make the following observation. So I'm going to say a metrics or a minimum spanning tree on a complete graph on a metric space. Or actually, it's actually true of a minimum spanning tree on any graph. Has a sum of edge lengths that does not exceed traveling salesperson on that graph. So actually, this is a more general fact about any graph. But just to show you an example here, I came up with what I think is a minimum spanning tree ahead of time, which you can compute with Kruskal's algorithm, for example. And certainly you could compute a minimum spanning tree on a complete graph in a metric space as well using Kruskal's algorithm. And here's a spanning tree. Okay, so the claim here is that the sum of these edge lengths does not exceed the length of any traveling salesperson path. So the shortest one cycle that I could come up with. Now, because I have the complete graph here, so any possible edge, actually any permutation is a valid cycle here. So I can consider anything. So maybe let me just say, maybe I do 0, 1, 2, 4, 3, 7, 5, 6. So there's a permutation. And so what does that look like in the graph? So that would be 0, 1. So again, this edge is there even though I'm not drawing it because every edge is there in a complete graph. 0, 1, 2, 4, 4, 3, 3, 7, 7, 5, 5, 6, and then 6 loops back to 0. So if I were to highlight that, then what you would see is the following path here. So here's I don't know if it's a traveling salesperson path. I'm not sure if this is the shortest one I could do, but there's one. And so looking at the edge length, somehow the sum of the red edge lengths does not exceed the sum of the black edge lengths. And the reason for that is actually even before I consider the last hop. So let's just say I went this far. So even before I consider the last hop, I've already at least done what the minimum spanning tree would have done in terms of length. And the reason is, well, because by definition, the minimum spanning tree is a tree that spans all the vertices. So it has one connected component thread, everything. And that minimizes the sum of the edge lengths. Well, I can see this path up to this point is a tree, right? It's kind of a boring tree. It doesn't branch out at all, but it's a tree. And then, so I know because it's a tree, it could not be any less than the length of a minimum spanning tree. So maybe it is a minimum spanning tree, who knows, but it certainly couldn't be less than that. And then actually, I'm going to add another edge too. And so it's going to be even longer. So anyway, that's why we have that a minimum spanning tree has a sum of edge lengths that does not exceed a traveling salesperson. So the traveling salesperson is at least as long as the minimum spanning tree. Okay, so that's the idea. So that's cool. And actually, we can use this fact to devise an algorithm, which I'll call two approximation of a traveling salesperson on complete metric graph. And what the algorithm does is the following. So first, you compute an MST on that complete metric graph, and then the second step is pick any vertex on the MST and do a depth first search on the MST. And then the claim is that the order of the vertices, the order that the vertices are visited in the DFS gives a permutation whose length does not exceed twice a TSP permutation. Right? So we're going to be able, from this algorithm, to come up with a permutation whose length is not twice, is no worse than twice as bad as the best that I could have done. So let me just show you why by walking through an example here. So I'll consider, maybe I start at 0. So I'm going to do a depth first search, and I'll keep track of the frontier here, and I'll keep track of the order that the vertices comes out. So let's say that I start at 0. Okay, so 0 is on the frontier. So 0 comes out of the frontier off the back there, and then we add the neighbor of 0, which is 2. There's just one neighbor there. All right, so now 2 comes off the frontier. I'll keep track of that. That's the next one that comes out. And I add 2's neighbors. So 2's neighbors in no particular order, 1, 3, 5. Whoops, 1, 3, 5. Okay. So that's great. 1, 3, 5 are on the frontier now. So 5 is the one at the end. 5 is going to come off next. So 5 comes off the frontier. I add 5's neighbors that aren't already visited or on the frontier. That would just be 6 here. So then 6 comes off the frontier. 6 actually doesn't have any neighbors that haven't already been visited or on the frontier. So 6 comes off the frontier. Then 3 comes off the frontier. When 3 comes off the frontier, I add its neighbors 4 and 7. And so then 7 comes off the frontier. Nothing to add there. And 4 comes off the frontier. Nothing to add there. And then finally 1 comes off the frontier. All right, so that gives us a permutation. That was me following through the algorithm. And so my claim is that the length of this never exceeds twice the length of an actual traveling salesperson path. And so to see this, I'm going to prove something different first. I'm going to prove that this length does not exceed twice of the minimum spanning tree length. Okay, so that's the thing I'm going to prove first. And if I can prove that, then I'll just use that inequality that I already came up with. And then I'll complete the proof. So let me focus on proving that this path has a length that does not exceed the length of the minimum spanning tree. Okay, so I see 0, 2, 2, 5. So I'm staying so far along the minimum spanning tree, so that's cool. 0, 2, 2, 5, 5, 6. That's great. Now here's where it gets a little bit interesting. Now I'm going to follow an edge that was not in the minimum spanning tree. Okay. And so those are the edges that I really have to pay attention to. All right, so I did 0, 2, 2, 5, 5, 6, 6, 3. Now I'm going to do 3, 7. That's in the minimum spanning tree, so that's lucky. But then 7, 4, I leave the minimum spanning tree. And then 4, 1. And then finally, I'll connect 1 to 0. Okay, so there's my path, and it doesn't look too bad. But how do I prove that the length of this path doesn't exceed the length of the minimum spanning tree? So one thing I have to do is kind of think of these edges in two different groups. One group of edges is the edges that are in the tree. So I'll make a little legend here. So we have, sometimes we use edges that are in the tree. And sometimes we actually take shortcuts. And we really need to look at these shortcuts here. And so to analyze the shortcuts, I'm going to compare them to what I would do if I forced you to stay inside of the minimum spanning tree. So this shortcut from 6 to 3, if I were to walk along the minimum spanning tree, I would go 6, 5, 5, 2, 2, 3, right? So I would go along that path. maybe let me draw that in blue here. And in this shortcut from 7 to 4, I would go, if I forced you to stay in the tree, I would go 7, 3, 3, 4. So I'm going to try to force myself to stay in the tree because those are the edge lengths that I'm trying to relate this to. So let me stay in the tree here. And then one more that I have here, this is going, oh, actually two more. I need the shortcut from 4 to 1, so then I would go 4, 3, 3, 2, 2, 1. So that would be how I would move between those, staying actually in the tree. And then finally, I have this one that completes the cycle. I actually took a shortcut there from 0 to 1. So to get from 0 to 1, I would or 1 to 0, I would go 1, 2, 0, just like that. Okay, so let's look at these. And so what I've done here is I've shown kind of another path that I could have done that retraces some of the edges of the minimum spanning tree. And so I have the shortcuts, but really I'm going to look at, as a proxy to those shortcuts I took, I'm really going to consider the equivalent paths that I could have taken in the minimum spanning tree. So let me say here, okay, so these are the equivalent paths. And so what I want you to notice, if I look at each edge in the original minimum spanning tree, so let's look at the edge between 0 and 2, for example. So I notice that I count that once as an edge that's actually in the tree that I use, and I count that another time along an equivalent path. Let's look at the edge from 2 to 5. Yeah, so I count that edge once, actually using it as an edge in the tree, and then I count it another time using it along an equivalent path. Looking at the edge from 2 to 3, I actually count that once along an equivalent path and once along another equivalent path. And so what you notice here is that each edge, so considering the union of all edges in the tree and edges along equivalent paths, whoops, sorry, my head was above that. We count each MST edge exactly twice. Okay? So each edge in the minimum spanning tree gets counted exactly twice when we consider these edges, the edges that are in the tree, and the equivalent paths that we construct when we force you to stay inside the minimum spanning tree. Okay, so there's that number 2 showing up. Somehow I'm counting twice this. Now what I want you to notice is if I use the equivalent paths instead of the shortcuts, that's at least as long as using the shortcuts, because we're in a metric space, because we have the triangle inequality. That's why I called these shortcuts. So if I were to force you to use these blue paths instead of the shortcuts, and when I do that, including all the blue paths and the edges in the tree, I count the MST exactly twice. That's going to be longer than if I had taken the shortcuts, because we're in a metric space. And so that's how I can prove that the sum of the red lengths is no longer than twice the MST. Because I count the MST twice using these equivalent paths, which are actually could be a little bit longer than the actual shortcuts I choose. So therefore, in the end, what I have is that the length of this, maybe I'll call it, maybe I'll call this permutation P prime. So the length of P prime is less than or equal to the length of the MST times 2. And we already established that the length of the MST is less than or equal to the length of the traveling salesperson path. So that's certainly also then less than or equal to 2 times the length of an actual traveling salesperson path. And so that's what proves this. So there we have it, a nice simple algorithm. And it's actually quite efficient too, because so computing the MST, this is going to take time. Well, if you think about what the algorithm does, it has to sort all, if we're doing Kruskal's, for example, this has to sort all of the edges. And so there are E log E edges. Actually, in a complete graph, E is V squared. So, but when you take the log of a square, that comes out as a constant in front. And we don't actually care about constants. So to do the sorting, it would be E log V to sort the edges. And so actually, you know, if we're in a complete graph, that's really V squared log V. But and then we're going to run you know, union find to add edges and make sure we don't have cycles and all that, and Kruskal's algorithm. Well, that's going to be V squared log star of V, or V squared inverse Ackermann V, which is actually smaller than log V. So the dominant cost there is V squared log V. And then depth first search, well, I mean, the MST has V minus 1 edges. We saw that the depth first search took big O of V plus E time. So actually the depth first search is going to take big O of V time, going through each of V vertices and each of V minus 1 edges. So actually, boy, this is really lightning fast to enumerate the permutation once you've computed the minimum spanning tree. So computing the minimum spanning tree is the dominant cost of this algorithm, but it's not too bad. It's polynomial time, and it's something we can do, even though the original problem in general is very inefficient. So that's it. So what I'm going to talk about next is a couple ways to improve this in the case that these vertices are in the plane. So I'm going to give you a couple of tricks, and then I'll talk about another trick that's used to clean this up, even in any metric space, that you can still clean this up. Okay, so that's it for now. As I was cleaning up my notes here, I realized I did forget one little thing in my definition of a metric space, which I kind of assumed because of the kind of graphs we were looking at, but it is important also to say that that the length of any edge is not negative. So maybe I'll say 1b here. It's a bit awkward, but the length of any edge is greater than or equal to 0. I don't want to have negative edge lengths. We will actually talk about negative edge lengths towards the end of the course, but for now I'm considering only non-negative edge lengths. Okay, so that was one little caveat there.